Thank you so much, Lisa. Thank you so much for planetary thinking. And not only Lisa, but also other indeed, Katarina, Klaus, Frederick, and Fabrizio, for the opportunity to share the stage today with many other amazing speakers. And my role today, I would say, is to introduce a little bit our keynote speaker and to provide a little bit of extra context in my response to his main keynote. Just to briefly introduce myself, my name is Lukáš Likavčan. I come from Slovakia. I'm a philosopher focused on emerging technologies, ecology, and astronomy. So if you will, I kind of oscillate very often between the planetary and the extraplanetary context of thinking, because in my work, I usually trace, I would say, intertwined histories of scientific infrastructures, but also ideas and cultures that inform our efforts to maintain planetary habitability. So if you want, I mean, I'm doing something like rethinking ecology without after outside or beyond nature. I'm a researcher at Slovak Academy of Sciences and also the Extra think tank, which is supported by Berkeley Institute. And I also teach at Design Academy Eindhoven and at UAL as some like things in London. When it comes to planetary thinking, I'm a former fellow of the panel. And I spent the last days sitting long days at the office at the Likavčan, writing, among other things, also this paper. And it's a paper which is co-authored by our main keynote speaker today, and I'll introduce him in a great detail a little bit later. Another important paper here is this essay, which Adam wrote for the Berkeley Prize, and actually he won the Berkeley Prize, which was the context and essay context at the Berkeley Institute for the best essay about planetary thinking. And so here we see our keynote speaker. So Adam is Helen F. and Fred H. Golding Professor in the Department of Physics and Astronomy at the University of Rochester. He belongs to the world's leading astrophysicists and astrobiologists, and his computational research group at the University of Rochester has developed advanced computer tools using the studies of star formation or the evolution of exoplanet atmospheres. Much of his current work focuses on how life and planets evolve together, which is a topic he develops as the principal investigator of NASA's first program to study the planetary scale of technosignatures, which is a concept that he's going to introduce a little bit in a moment. Adam is also an avid writer and public commentator, as documented by his non-listed written contributions to the New York Times or the Atlantic, as well as his fine books, most recently The Little Book of Dreams and The Blind Spot, which is co-authored with Marcelo Gleiser and Ivan Kossen. And with that, I pass the mic to Ryan, so please give him a round of applause.
Yes, good. Okay, so how do we switch?
Great. Thank you very much for inviting me to this. I've already found the discussion fascinating. So I'm really looking forward to sort of, telling you guys about what I've been working on, and framing this idea of planetary intelligence and the idea of mature technospheres as part of the conversation, but also, listening to the other talks as well for the time that I'm here. So one thing before we start, I am from the New York metropolitan area, so I speak very quickly unless somebody tells me not to. So please, if I'm going too fast, raise your hand and let me know, and I'll slow down. I'll reduce my bullet rate. Okay, so the topic here is this idea of the overlap between astrobiology and the Anthropocene. This is something I've been working on for a while. And in particular, what I want to do is frame the relationship between, thinking generally about what's happening to the Earth and the human project of civilization, for lack of a better term, as kind of something perhaps more general than just focusing on what's, on our specific case. That perhaps the Anthropocene is actually an example of something that may be quite common in the universe. And that thinking along those lines may give us some insights about what the future might hold for us. So basically what I'm going to be telling you about is based on a few papers that are things I've written over the last few years. First of all, this paper that I co-wrote with David Grinspoon and Sarah Walker, both of whom are astrobiologists, called Planetary Intelligence, or Intelligence as a Planetary Scale Process. The second thing is this, the coming second Copernican Revolution, which is that Berggruen essay I wrote. And then finally also the paper that Lukáš and I just completed, The Planetary and its Uses, Grounding Political Economy in an Astrobiological Perspective. So that's what's going to frame these three papers, what I'm talking about. And so this idea of planetary intelligence, I'm going to sort of discuss this as a way of thinking about how species and how biospheres, technospheres, and geospheres, the rest of the planets, evolve. Both what's happened on Earth and also what perhaps is quite universal. Okay, so intelligence. How do we think about intelligence in terms of Earth's history? Well, it is often thought of that the appearance of intelligence represented a major transition in Earth's evolutionary history. There's this paper by Smith and Sazanari from back in the 90s, where they tried to lay out the fundamental changes in Earth's evolution, or the evolution of life. And you can see things like the replicating molecules. That was the first one, was the starting right. The RNA to DNA, that was a transition that fundamentally changed how life would work. And then you see somewhere down there, primate societies to human societies, right? So in this telling, intelligence is a fundamental transition, but it happens very, very late. And actually, I'm going to argue that we should be thinking about intelligence much more broadly in terms of planets and planetary evolution. So that leads to the question of who or what has intelligence. And conventionally, we think of it as something that individuals have, right? Dolphins, human beings. Intelligence is up here in a brain. And it may also, though now recently, or at least the last couple of decades, you come to really recognize that it's also could be a property of collectives, right? Collective decision made by social insects here. An ant colony is one representation. But actually, we recognize that it's much broader, this collective property of intelligence, collective intelligence, maybe much broader than just, termite mounds. So for example, the example of slime molds, right? Slime molds are basically single-celled organisms. And it's been found that slime molds actually have this capacity to do enormous cognitive processing, like solving mazes. Bacteria also, very low on the hierarchy of life. Bacteria actually act communally and have been recognized to act cognitively, meaning they don't just bump into their surroundings. They actually, are aware of their surroundings and can respond collectively to their stuff. So this is the idea of quorum sensing. If you have enough bacteria acting together, then collectively they will respond to threats by changing their chemical outputs, etc. And then recently there's been this beautiful work about, the wood wide web, the idea of forests as being, it's not the tree that is the living thing or the entity, it's the forest. And that there's evidence that forests can, through the mycorrhizal networks, the fungal networks, will actually transport resources to parts of the forest that are under stress. Now, recently, this has been challenged by some new work, which is great, because the idea is so awesome that, if you really want it to be scientifically true, you need pushback. So I personally hope that it survives the pushback, but, we'll see, right? But it's because it's such a potent idea. Okay, so what from these last two slides, we want to add the idea to intelligence, that intelligence broadly construed, I'm not talking about necessarily self-consciousness, I'm talking about cognition, a knowing of and responding to, it operates across really a wide range of length and time scales, right? So forests can be, hundreds of miles across. And if that is the entity that we need to be thinking of, clearly we have now collective intelligence operating on quite large length scales. So the question that we want to ask is, can intelligence operate at the planetary scale, across planetary length and time scales? And if so, what does that transition look like, right? Because Earth started off without life, so therefore there was no kind of planetary scale intelligence. But at what point, if this is true, did Earth sort of make that transition to planetary scale intelligence? And the consequence of this would be amazing, right? Because it would show that, if this was true, that the biosphere itself has some degree of cognition. Again, it's not like the biosphere is thinking something or has self-consciousness. But what it would mean is that in some sense, I'll frame it this way. Intelligence is not something that occurs on a planet, but to a planet, right? It's part of this fundamental transition that a planet goes through when it develops life, right? Because we know, as we'll talk about, once you develop a biosphere, the biosphere hijacks the planet. And on the one example we have of this, we know that the Earth's history was utterly changed by having a biosphere. And we expect, as an astrobiologist looking for life in the universe, that's our expectation. In fact, that's how we're going to find life. We're not going to find, if I'm looking for life on a distant exoplanet, I'm not looking for, a critter on planet Zorgon 26, right? I won't be able to see that. My telescopes can't see that. What I'll be looking for is the cumulative effect of the biosphere on the planet. And I'll talk about that more. So the question here is, why ask this question about planetary intelligence at all? And it turns out that the concept is useful for three distinct domains. Thinking about Earth system science, which also means thinking about exoplanet system science, Anthropocene and sustainability studies, which is what we're interested in, but also the search for intelligent life, the search for any kind of life, but also in particular, the search for intelligent life. So what we can now call technosignatures. It used to be called SETI, Search for Extraterrestrial Intelligence, but now we call it technosignatures. So let's just go through these three. So Earth system science. So here is, when I show this slide, I ask which one of these is Earth, right? And the joke is, they're all Earth, right? They're all Earth at different points. So the Earth has had this amazing history. It was early on, it was a molten planet. There for a while, there were no continents, not really. It was a water world. And there were periods when it's been a jungle world where there's been no snow anywhere. There's been periods when it was all snow, it was glaciated. Here's the Earth now, and here, sadly, is the Earth in about 2 billion years. Okay? So the oceans have boiled off. And life really drove many of these transitions. That's the interesting thing. Now, when it comes to exoplanets, here is a plot, this is the plot we all of us astronomers show. Here is size of planets, and here is orbital period or distance from, and these are just a small sampling of all the planets we found. We now know about 5,000 planets in the universe. And that's enough to do statistics. And so what we now know is that when you go out and look at the stars at night, every planet or every star you look at hosts a family of worlds. Every one. Every star has planets. And if you count up 5 of them, one of those stars has a planet orbiting in the right place for life, what we call the habitable zone. Stunning conclusion, right? And the thing about whether there's life or not, I can tell you for sure that some of those planets, there'll be snow drifting across mountain valleys. There will be rivers running, across plains. That for sure. Now, whether there's life or not is an open question. But all these different planets, there will be oceans. There will be shorelines. There will be snow-capped mountains. And when it comes to Anthropocene and sustainability studies, this question of planetary intelligence. So, my point is the question of planetary intelligence is relevant to all of these, including Anthropocene and sustainability studies, because I love this. This is a paper by Axel Kleiden. If you look down here, you see this is like the total energy being used in these different processes. And so on the Earth, the total amount of biospheric energy use is about 152 plus 63, about 200 terawatts, right? Every day, there's 200 terawatts being used. And the human consumption of that, the human appropriation of that is 50. So right now, human beings, what I call the project of civilization, is using a quarter of the total biospheric appropriation or the total biospheric energy use from solar or the sunlight. That's incredible, right? Of course we changed the planet, right? You're going to use that much energy. Of course you shifted the planet responded, right? Okay, So now I want to talk specific. So my argument is that the idea of planetary intelligence is relevant to all three of those things I said. And now I want to talk to you a little bit about what planetary intelligence is, the idea behind it, and why, and then we'll get to why it's relevant for our thinking about sustainability. A historical preliminary it starts with Vladimir Vernadsky, the great Russian biogeophysicist. He basically invented biogeophysics, and he was the first one to actually really make the word biosphere, to popularize or really think about the biosphere. A series of lectures from Paris in the 1920s where he really laid out the idea of the biosphere, that like life is not some pond scum, on the surface of the earth. It is as he said, it's a geophysical force. So he was the first one to recognize that. And then with James Lovelock and Lynn Margulis came Gaia theory, right? The idea that, the planet, the biosphere actually is not just a force, it is perhaps the dominant force, even the guiding force for the planet's evolution. So actually, this is a great picture because here, this is James Lovelock's land, and that is a statue of Gaia. Okay, so let's talk about Gaia theory. The idea here is that the biosphere co-evolves with the geospheres, and that in some sense it is so potent that it sort of makes Earth into a self-regulating homeostatic system. Basically, life hijacks the evolution of the planet and maintains the planet in a state that is good for life, right? If you perturb the system, if an asteroid hits the Earth or, somehow you get out of chemical equilibrium or chemical balance, that the biosphere will start driving feedback mechanisms that damps out the perturbation, right? Temperature gets too high, some kind of microbe starts growing that actually will change the planetary the atmospheric chemistry, brings the temperature back down. So there was this kind of idea that, the Earth is a living entity. The Earth is like a cell. And I'm going to say, well, kind of, because this was sort of the problem when Gaia was first introduced in the late 70s and 80s. It became way more popular culturally than it was with scientists. And part of the reason was this. These I'd like to introduce you to Oberon and Morning Glory Zell Ravenheart, who were priests of Gaia, right? So the thing about Gaia is there's starting to be Gaia festivals and Gaia Gaia's church services. And so you look so these are priests of Gaia. And if you look at this, yes, that is actually a unicorn. Well, actually, it's a sheep with a horn to lead to its forehead. But it's sort of, this is what the problem that scientists had. Some part of the problem was that it had become sort of this very new age thing. But even more, the real problem, and it's going to be important for us, with Gaia was that people said the scientists pushed back because it was too teleological, right? It was the idea that the Earth wants something. And, they would argue that, evolution never wants anything. Evolution is blind. But as we're going to see, this issue of teleology is going to come back to us because once it's true that in general, evolution doesn't want any. But actually, when you sort of think about intelligence does want things. Intelligence does have goals. You can frame it that way. The interesting thing that happened with Gaia, so by the late 1980s, Gaia was very much rejected by the scientific establishment, but by the late 1980s, it was recognized that, there was a really good idea with Gaia. So what people did is sort of switched the name, right? We switched out the name Gaia and we adopted the name Earth System Science. And it became the foundation for climate studies, right? And there's now, there's a lot of great papers where they really recognize the debt that Earth System Science owes to Gaia theory. One problem with Gaia theory is that we still don't have any proof of that true self-regulation. We know that the biosphere has massive impacts, exerts massive controls on the planetary evolution, but whether or not there's actually a homeostatic feedback is still debatable. This is a little representation of Earth system science. You see these different systems, starting at the bottom to the right, the atmosphere, the hydrosphere, the cryosphere. You have to treat ice as a separate system. The lithosphere, which is the land that we actually interact with, and then the biosphere. They're all tightly coupled systems. And so the biosphere matters. That's what came out of Gaia theory and that Earth system science picked up on. And in fact, biospheres matter so much that they can alter the entire history of the planet, right? And so the greatest example of this, and the example that's most relevant to try to generalize what happened on Earth to all the other planets in the universe is the Great Oxidation Event. So this is a plot of time going backwards. This is 4 billion years ago. And this is the oxygen content in the atmosphere in log units. So what you see is back there at 4 billion years ago, there was 1/1,000,000th of the current level of oxygen in the atmosphere. Basically, there was no oxygen in the atmosphere. And you go through, 2 billion years, and there's still no oxygen in the atmosphere. So what that means is if you were to land on Earth 2.5 billion years ago, you would have found a planet where there was life. There was, lots of microbial colonies and everything. And as you walked out of your spaceship, the first thing that would happen is you'd die because there was no oxygen. There was life, but there was no oxygen. So then, all of a sudden, you see the oxygen climbing up here, going up by a factor of, 10,000, and then climbing again. And what did that? It was life. Basically, evolution stumbled upon a new form of photosynthesis that used water as the substrate. And then what it would do is it would basically take a water molecule, break it apart, use the hydrogen atoms to make a sugar molecule, and then it farted out the oxygen, basically. And so the planet just filled up with oxygen. And so this oxygen increase here, the Great Oxidation Event, was probably the most important event in the history of the planet on a certain level. Having oxygen in the oceans and in the atmosphere completely changed the planet's evolution. The important thing to note also is the species that did this, that was not great for the species that did this. It basically, the species that created the Great Oxidation Event, oxygen was bad for it. And where is it now? It's in our guts in non-oxygenated environments, or it's deep under the sand. So, this was an extinction level event, almost, made it through. But for the creatures that changed the planet's atmosphere, ended up suffering because of that change. Does that sound familiar to anybody? Right? A species doing that? So that's a kind of an important point, right? This has happened before. It just wasn't happened with a self-conscious species. All right, so where I'm going now, before I go further, I have to stop for a moment and just, because not all of you are astronomers, I need to tell you what spectra are. What I mean by spectra, because it's going to be really important. So, the way astronomers figure anything out about the universe is we look at light. We take light, that's all we get is light from distant objects. We pass it through a prism, basically, that separates the light out into its colors. So here's a little diagram. Here's a star. Here's a planet with an atmosphere. The starlight is passing through the atmosphere. And when it passes through the atmosphere, the light from the star will be absorbed by the chemicals in the atmosphere, right? So you see there's all these different colors of starlight, but then there's all these jags in there. There's all these different little bites. And what's happening here is at all of these different wavelengths, all these different colors, you're seeing compounds in the atmosphere sucking up light from the star, right? And so that there's a fingerprint. Basically what you're seeing is kind of a spectral fingerprint of titanium oxide, of water, of water, everything. So that's how we figure out what's in an atmosphere. We actually can see the light passing through a distant planet's atmosphere and use that, and then we can see the fingerprints of all the chemicals that are in the atmosphere. Why am I telling you that? Because I'm going to come back to this idea of spectra later. But it's basically how we are searching for biology and technology on exoplanets, right? What we need, what are called biosignatures and technosignatures. The main way we're doing it is we are looking for the light from the star passing through the atmosphere, and then we'll be able to see the spectral fingerprint of carbon dioxide, methane, oxygen, chlorofluorocarbons, right? We can do that. We can actually look for chlorofluorocarbons, which can only be produced by technology. All of this we can do with things like the James Webb Space Telescope. So what we're looking for in the light from distant stars is signatures of a biosphere or signatures of a technosphere. Okay. So that gives me the background that I need to now tell you about this thesis that Gaian planets, that actually any planet that has a biosphere that is long-lived, must be Gaian in the sense that it is going to have these incredible dense web of feedbacks between all the different kinds of life, and the other systems, the atmosphere, oceans, etc. And that actually is what we mean by planetary intelligence. So, so this is the idea. Basically, is that any planet with a long-lived biosphere will be guiding, and what that really means is it will host planetary intelligence. So what do I mean by planetary intelligence, right? So I'm going to give you that paper, we sort of articulated 5 properties that this kind of planetary scale cognition would have to embrace. And they are emergence. Planetary intelligence would be an emergent phenomena. It would be represented as a flow of information across networks. That information is not just the kind you use in your computer. It would be semantic information that carries meaning. The whole system would have to be what's called the complex adaptive system. And finally, and most importantly, the system would have to be autopoietic. And I will explain what that means in a second. So I'm just going to go over a couple of these. So what is emergence, right? Emergence is this absolutely critical idea that completely changes how we think about life. An emergent system is one that is collective property where you have atoms. Sure, you're built out of atoms, but that's not enough to explain what you are. So this diagram sort of shows you what we mean by emergence. This is scale, right? So at the bottom level it's a hierarchy of organization. At the bottom level, you got atoms, right? But those atoms, let's think about a body. Those atoms are organized into things like cells. The cells are organized into things like organs, and the organs are organized into the animal, the entity, right? And so complex emergence is the idea that this thing that gets organized, that final state of organization, cannot be predicted by the lower levels, right? If I knew every atom, where every atom in your body was, and where, what the motions of every atom in your body was, I cannot predict you, right? This is a fundamentally, fundamental transition in how we think about the world, right? I'm a physicist, trained as a theoretical physicist. And what I learned was, reductionism. The world is just made out of its atoms. That river that we want to talk to, come on, the river is just a bunch of atoms flowing along. It's dead. It's made of dead atoms. Emergence is an important idea because it says that when things get together, when you accumulate lots of these lower level entities, true novelty can appear, right? And so I have these 2 arrows. So, these arrows are important because normally in physics, we think of everything as top or bottom up causation. If I know the laws of the atoms, I'm done. But really what emergence tells you is you can have top down causality as well. Once you create something like an animal, those electrons can be herded into behaviors that you would never predict from the lower levels. So that's an important idea. Another important idea is this idea of information flow on networks. Planetary intelligence will really be about networks of actors, networks of processes that are linked together where information is flowing across them. So this is just a basic idea of a network. You've got nodes with the circles and edges, which are telling you about the relationship. So this is also telling you that planetary intelligence is all going to be about relationships. Right? That's the change. Rather than in the old school physics, everything was about ontologies. Everything was about, atoms. It wasn't, that was the important part. Atoms and their properties, not relationships to other atoms. So, I don't need to go through this too much. These are just 3 different examples of networks. The important thing about networks is that the language of networks is universal. I could be talking about a gene regulatory network, or I could be talking about your social network. Exact same sort of conceptual mathematical formalism. So, for example, here is a food web in a pond, right? The structure is always the same. So whatever we mean by planetary intelligence, we're going to think of it in terms of, these vast interconnected sets of processes that are feeding back always. They're transferring information back and forth. And it's that transfer of information that is the important part for the intelligence, right? And that's why I'm not going to go into semantic information. But when we talk about information, there needs to be a knower, right? If information always assumes that there's something known, but somebody knows it, right? And so the idea is that the biosphere, a Gaian biosphere, is all about the information, which means that the biosphere on some level knows things, right? And finally, this is the most important point. I don't know if you guys are aware of this, but I fallen in love with the idea of autopoiesis. It was the work of the Chilean biologists Monterrada and Francisco Varela, and it was the idea of self-creation. So not only do you have life is not only a network, but it's a self-organized, self-maintaining, self-creating network. So here's, a bunch of, this is an abstract representation of a bunch of processes. A process or an entity is autopoietic if every part of that network refers back to itself, right? Living systems are fundamentally autopoietic. And I'm going to tell you right now, this is, I've been working on this in the new physics of life. We don't really have a handle on what autopoiesis is, right? We don't have a handle on what that kind of organization is like. Sometimes the word that we use is causal closure, that life causes itself. All of the causes that link back to itself. This is why life is not like a machine. Life is fundamentally different from machines because it is autopoietic. Okay, so because of this is where significance and meaning appears. Once you become a unity, right? All life is a unity. It's a whole. Now, it is an entity that the world has relevance for it, right? A large language model, nothing's relevant to a large language model. There's nobody in there, right? It's only life it's only life for which things are meaningful. Only life has an itch to scratch, right? So this autopoiesis is going to be very important because it's, autopoiesis is sort of the closing part of something being intelligent, being sentient. And so now we want to think about planets having this property. So now I want to introduce you to this idea of immature and mature biospheres. And so the question we might want to ask is, okay, intelligence, right? Even before I get a technological species, which is clearly intelligent, can planetary scale intelligence operate on worlds without a technological species, right? Just a biosphere. And the answer, we would argue, is yes, because this is a diagram that shows the environment on one side, the planet on one side, and life on the other side. And it's been recognized for a while that the planet and life have been co-evolving. The biosphere affects the planet affects the biosphere, as we just talked about with the great oxidation events. So our answer is yes, planetary intelligence doesn't need a technological species because this coevolution of the coupled systems is what creates those networks of Gaian feedbacks. And as we already saw, it's this idea of information flow on networks that is going to be important. So this leads us to the idea of immature versus mature planetary systems, right? So this is all going to be about planetary intelligence. A mature biosphere, we're going to introduce that term. A mature biosphere is one that has established those self-regulating feedbacks. Mature means at this level, planetary scale, collective cognition has been established. So if we're going to talk about mature, we have to first understand what immature means. So what is an immature biosphere? So this would be the Earth during the Archean. Life was thin on the ground, right? There wasn't a whole lot of life, so life was not able to exert a whole lot of geochemical forcings on it. And you'll see the planet was gray. It was a haze, right? The planet looked very different if you visited. So this is about 3.2 billion years ago. And if you looked at a spectra of the planet, right? So this is brightness versus wavelength. What you'd see is you could find there was CO2 there for sure, and there was methane there for sure, but none of these were really due to life. This was all, life wasn't changing anything yet. Wait another few billion years, and you get the Earth, say half a billion years ago. This probably happened, the Gaian feedbacks probably is happening much earlier than this. And now what you see is, a planet that has a rich biosphere, that is really shaping the planet's evolution. And you could see this, if you were looking from a distance, because you'd find oxygen in the atmosphere, right? If it wasn't for life, oxygenic atmosphere would disappear on the scale of 100,000, maybe a million years. It would all get bound up to the rocks. So if you see a planet with oxygen in its spectra, you're like, whoa, there's a biosphere there. That is our Uber or biosignature, seeing oxygen. So this is a planet, the fact that you're seeing oxygen in the atmosphere is indicative that the planet has reached this state of maturity, meaning those Gaian feedbacks have all settled in, and it is this idea of planetary intelligence has been established. The planet is a dense network of interacting processes such that you can think of it in terms as it's a system that cognates, right? Again, no self-consciousness. It's not like Gaia is making decisions for itself or singing to itself, but that we can think of it as a system with a collective cognition, which are those feedbacks. So again, so if I go remember those 5 properties I gave you? You can go through the Earth, 500 million years ago, and it's got all emergence, yes, information flow on networks, yes, semantic information, etc. So the mature biospheres possess planetary intelligence. That's the idea. And we've started working on mathematical models for each of these, trying to understand like when this would occur. All right, so now let's switch over and start talking about technospheres. So, you guys all know what a technosphere is, but just, to quote your path, technospheres are interlinked sets of communication, transportation, bureaucratic, and other systems that act to metabolize fossil fuels and other energy sources. Okay? And so this is this beautiful image of the world shipping, right? That's a network, right? That's a pretty profound network you're seeing here on the show. So, technospheres. Are technospheres examples of planetary intelligence? On the one level, you'd be like, well, of course there's intelligence there, right? The species that's creating those shipping containers and the ships is intelligence, but does that mean that there's planetary intelligence? And the answer I want to give you is that, like, really right now, and we're going to come back to this a bunch of times, what we have is an immature technosphere. Just like we could talk about an immature biosphere, what we have now is an immature technosphere. So if you look at, say, the spectra of the Earth now, there's a satellite, it's clear. That's an amazing thing, right, about satellites. For the first time in the history of the planet, something's leaving the planet. The entire, 5 billion years of planetary history, stuff only went down the gravity well. So this idea that we're starting to throw stuff out of the gravity well shows you something new is truly happening. But if you look at the spectrum, you see CO2. In fact, you see more CO2 than you had before the technosphere was emerging. You see oxygen still, that hasn't changed. You see methane. But now you got these new things, like chlorofluorocarbons, right? So it's clear that the planet, that there is a technosphere. You could see the chlorofluorocarbons on Earth right now from a distant planet. But if we looked at the system in detail, what we would find is that, it's got emergence for sure. It's got information flow on networks. There is certainly the information that's being cast around has meaning to the creatures that are creating the technosphere. It's a complex system, but it's not autopoietic, right? The system is destroying the conditions that it needs to survive. Autopoiesis is always about, creating this whole that maintains itself. Autopoietic systems are self-maintaining, right? Self-creating and self-maintaining. And clearly, the current technosphere is destroying what it needs to be able to endure. So what that means is, our current early Anthropocene phase displays key features of planetary intelligence, but it's not there yet. It lacks autopoietic self-maintenance. And so that's why this idea of autopoiesis is so important. So what we're looking for, what we want, is a mature technosphere, right? So we're imagining this planet in the future. There's, space station. There's all cool stuff that I want to, a little bit on. And you can see that now, actually, what's interesting about the mature technosphere, if you look at it spectrally, is you see that CO2 is being regulated, right? Where, a mature technosphere, the species that's running it, would be able to modify the atmosphere, certainly at least draw down CO2, so it's not, putting itself at risk. And there may be these other species, other chemical species, it's purposely putting into the atmosphere for whatever reasons it wants, right? So the interesting thing about this, so the mature technosphere would be a technosphere that was autopoietic. It was working in concert with the biosphere to not destroy its own conditions. And the interesting thing for me as an astrobiologist is this is what I need to be looking for, right? In general, if I'm going to find, technological civilizations, they have to be long-lived, just looking at the statistics, right? If every civilization lasts 200 years, then odds are I'm not going to find anybody because when I'm looking, they're gone, right? So the whole point of SETI and technosignatures assumes that there are old civilizations, which means they will be sustainable civilizations, which means they will be mature technospheres, which means they've achieved planetary intelligence. The technosphere and the biosphere have now come into some kind of unity so that the whole system remains autopoietic on geological timescales.
Right.
Okay, so just to summarize this, right? This is the idea that planetary intelligence is planetary evolution, right? If you have a biosphere and the biosphere is able to make that transition to have the Gaian feedback so that it can endure for a long time, then you would go from an immature to a mature biosphere. And then, if you get a species, a technological species that deploys technology, you would go from an immature technosphere to a mature technosphere. We hope that that's possible. We don't know that's possible. We've never found an example of a mature technosphere, but the idea here is this idea tells us what we need, right? So the good news about this idea is it sort of tells you what the goal is, right? When we think about sustainability, this from a planetary systems, planetary science perspective tells you exactly what you need to develop and where you're going. So the goal is, right, to get past the immature phase. So while our current early Anthropocene phase displays critical features, I've already put this, we lack self-maintenance. So self-maintenance is what it's about systematically. And so what we want is a mature technosphere that self-maintenance is obtained by reintegrating with the mature biosphere. Because you probably won't have a technosphere unless you have a mature biosphere already. So establish those feedbacks. That's what we mean by planetary intelligence. Okay. So I am almost out of time, so I'm going to go through this a little bit quickly. But okay, so that was the good news. Here's the bad news, right? This goal we had for so long of 1.5 degrees, we're going to blow through it. I don't think there's any debating that, which is remarkable thinking about like that. We were literally going to let it burn. So we're probably going to pass through those. And so what comes next, right? How do we deal with, right? So, well, clearly it's the end of the Holocene. We are passing out of the Holocene, and the sort of good Anthropocene, the soft landing we were hoping for, it's not clear we're going to get that. At least this is sort of where I'm thinking now. So what comes next? And for me, in thinking about, working towards a mature biosphere to developing planetary intelligence, the idea that I have is sort of the idea of the climate cathedral. How do we deal with what's happening now that we find ourselves here? So that idea, I'm going to start off with this quote. It was a difficult time for humanity. And this quote actually comes from a book I read when I was in high school, A Distant Mirror. I don't know if anybody's ever seen this. This was by the famous historian Barbara Tuchman, and it's about the calamitous 14th century. The 14th century, and she opens like, this is like the opening quote, or it's somewhere near the opening. So I'll never forget, it was a difficult time to have. The 14th century was plague, all these good things, 100 Years' War, papal schism, and there was climate change happening as well with the Little Ice Age. It was a terrible time for humanity, which is, interesting to think about what we may be heading into. But also, what came out of it 100 years later was the 15th century, which was the end of feudalism, thanks, and the beginning of the Renaissance, right? So it's important to sort of have, as an astronomer, it's easy for me to think on long timescales, which, is good, but also doesn't see the suffering that is happening, right at the moment. But recognition that, history's long and, you don't know what's going to come out of what you're going through at that moment. So what I mean by the climate cathedral is the response to probably what is going to be decades ahead of us of instability in many ways. Certainly climate instability, and then all the political instability that we're already facing, but that climate change is going to make worse. So the metaphor of the cathedral is that cathedrals were multi-generational projects, right? There's the Cathedral of Milan. It was started in 1386, and they just finished it a while ago, right? It was a long project, multi-generational. And each generation didn't say, like the ones who started it weren't like, here's the plan, stick with the plan, right? They basically, the people who started it passed along an idea, a schema, and then each generation, did what it wanted to do with that plan. Because, building technology's changed, right? You're not going to use your great-great-great-great-great-grandfather's tools when you got better tools. So this metaphor, the construction of the mature technosphere, the mature, we kind of hoped we were going to be able to do it like, in 2 decades. Probably not. That's what I'm thinking now. It just is going to require too much of a profound reorganization of the human conception of itself. And that leads to, so it's going to take longer. And that leads to this idea of the planetary as a political economy. So this great book by Bentley Allen, where he shows that scientific cosmologies, the change of one scientific realm of thinking to another, actually played a huge role in political economies. So this is a quote from Lukáš about it. So what did Bentley mean? Emerging scientific cosmologies constrained and determined default perspectives on the institutional organization of international orders, the dynamics of geopolitical change, and the nature of international economic systems, right? So it's the scientific view, at least in the last 400 years, that shaped what was possible politically, not just technologically, but conceptually. So here's the example that Bentley Allen uses. Newton, the age of Newton gave rise to the idea politically of the balance of powers. Darwin emerges, and then suddenly there's this idea of the evolution of states. Cybernetics, more recently, which is sort of like post-World War II, the idea of you can manage your economies with enough data, like as if it was a giant computer. And so the idea that Lukáš and I were working with is that astrobiology is sort of this 21st century. The planetary is, we're talking about the planetary. It's no accident. This is also the era when we're thinking about life on other planets, when we can actually find life on other planets. So the planetary and astrobiology are one thing, and that holds the possibility of being the political economy for the 21st century or further, okay? So this is this paper that Lukáš and I wrote. I hope you'll read it. And again, this idea, what we did in that paper is we sort of took these 5 properties of planetary intelligence, and what we really meant by all this, or what we were pointing to, was the idea of metabolism. That fundamentally what we're talking about here is a different kind of way of thinking about the metabolism of the planet and the organization of your political economy. Okay. So what this means is, really, fundamentally, what we need is a new story of what political economy means, and that's the planetary. And, I'm interested in talking with people about this, but I sort of have the feeling that the next few decades, the next couple of generations are going to go through a hard time, that there's just, what's going to have to happen is, as someone said, you don't notice a living river until it's a dead river. Then you suddenly notice what you lost, and there may be, just because of our stupidity, we may need to sort of have that vision shoved down our throats, or else we're not going to respond. And out of that will be the emergence of a different kind of systems. Right? We were talking about money, right? The problems with money and the kind of a capitalist economies that we have. There are other kinds of capitalism. We just refuse to sort of, think about them, or other kinds of political economies. And it may require sort of us going through this difficult time to be able to see the alternative. And this is important about this idea of stories, because the usual story we get about human history is this idea of human history, which is the guns, germs, and steels. Human history is a universal march from small, unsophisticated but egalitarian tribes to larger, hierarchical, technological empires, right? But this new book, which I love and I highly recommend, The Dawn of Everything, by David Graeber and David Wengrow, they were like, no, actually, the last 30 years of anthropology and archaeology show that story, human beings have had many different kinds of political organization. They're constantly playing with political organization. And the idea that by 1 AD, everything was empires is just entirely wrong. Talk about a colonial view. That there were lots of other possibilities, and those other possibilities are what we can draw from as we sort of go through the crap that we're about to have to go through. So, for example, the mega sites in the Ukraine, these are huge city-sized structures where there probably had tens of thousands of people living, and there's no sign of hierarchy. There's no signs of a state controlling everybody's lives, right? So this is the idea no, you can have large human organizations without the need for hierarchy. Really incredible. The other piece here is from Australia, and this represents what was the recognition that the various Aboriginal tribes they've been in communication across huge distances for 65,000 years, right? So this idea that you have to have this hyper-organized, hierarchical organization for your technosphere, or else it just won't work. No, that's not necessarily true. So almost concluding, so really, the Holocene, we're passing out of the Holocene. And the important thing to understand, this is something that my colleagues at the Gruen have pointed out, that, really every one of our institutions, pretty much, even, the things we hold in our heads, how we've organized, human institutions are all the product of the Holocene, the last 10,000 years. States, economies, war, personal things, even marriage, family, religion, they are all Holocene constructs. And we are passing out of the Holocene, right? So what opportunities does that come with that? So what comes next? What traditionally, or, what we get is, and I think this may actually, something to talk about, may have been a mistake for those of us who were, arguing, or trying to bring the idea of talk to the public about climate change. It was like 1.5 degrees or extinction, right? So we were only offering people 1.5 degrees, under 1.5 degrees, or it's this. But, there's still going to be human beings on the planet 100 years from now. Even if we hit tipping points, human beings are not going to go extinct, right? That's the reality. Things are going to get very difficult, and there's going to be a lot of human suffering. But at this point, this picture is, you don't offer anybody any hope, and it sort of may have kept us from sort of thinking about what should we do if we go past 1.5 degrees. So the answer is, this is not, necessarily what we're leading to. In fact, if you look at the history of societal collapses, something I know a number of us here have thought about, in general, it doesn't look like this. But what we should be thinking about is this idea of a cathedral. What do we pass along to the next generations that they have the tools that they can work with as they try and navigate this difficult situation and hold climate change, hold global warming down as every 10th of a degree matters, right? So that eventually 50 years, 100 years from now, we've stabilized, right? And then we've started really developing a mature technosphere. So just to conclude, what we're interested in, the mature technosphere is the climate cathedral, is the thing we're trying to build. And what that will really be is an awakened world. It will be both cooperative and co-evolving with life, and it'll be an I-thou relationship with the biosphere, which is really about, fundamentally about compassion and about love. So I'll end there, and I thank you very much for your time.
Thank you for this fascinating topics, Adam, for all the insights. I would love to ask you to focus for a little while on the remarks that is going to follow Adam's insightful lecture, because I would like to perhaps open the discussion with a couple of, I would say, main questions and problems that we face now as scholars thinking about the planet otherwise. I'm going to start with relations, because this conference has in its title this phrase, from relations to politics. And so I want to start with relations a little bit also, because before we jump into politics and discussing politics, let's talk about relations in general first. So in his General Morphology of Organisms from 1866, Ernst Haeckel used the insights of evolutionary theory to retell the history of life on Earth as a story of environmental adaptation. And here we have his definition of ecology, which is actually the first definition of ecology ever given. Haeckel described it as the entire science of the relations of the organisms to its surrounding external world. And more than 150 years later, you learned actually a lot about the relationships between organisms and environments, even to the point that we can replicate and apply the principles of environmental relations to entirely new domains. And there is a long history, for example, of swarm robotics, which has been originally inspired by collective behavior, the collective intelligence, if you will, of ant colonies or beehives, collectives which are characterized by division of labor and intricate communication via chemical and geometrical patterns. There is mycorrhizal networks that Adam also mentioned, that will enable communication between trees in the forest. There are fluid hierarchies and rules of thumb which are used, for example, by birds or sheep that they follow when they, for example, gather or move in groups. And basically, in each of these cases, what we see that populations of limited individuals, just as us, manifest collective agency that transcends their individual boundaries. And this brings me to a story, which is a reference that I have been repeatedly returning to in my recent writing. It is a true story about a Japanese robot whose name is Gakutetsuku. It is a robot which was built by a biologist, Makoto Nishimura, in Osaka in 1920s. And the robot got sadly lost and never found again, but rest assured, it really exists, or at least it existed at some point in history. And the story of Gakutetsuku reminds me how often technological innovation is actually driven by the desire to mirror the more than human, not the human nature. The name of the robot translates to English as learning from the laws of nature, and Nishimura constructed it with the ambition to embody the capacity to know the world, act in accordance with this knowledge, and carry it forward. And for this reason, Gakutetsuku, his task wasn't to, let's say, do some harsh manual labor. The task was to write spiritual texts. What a refreshing technological imagination, I tend to say. Keep Gakutetsuku in mind now, because somehow the robot story brings me to a paper that follows up on a lot of the work I've been doing with Adam. So this paper will be released on Friday. It's a paper that's going to be published in the Antikythera Journal, in the second issue of the Antikythera Journal, which is published in collaboration with MIT Press. And the name of the paper is The Log L. The paper is motivated by a quote by Freeman Dyson that every search for alien civilization should be planned to give interesting results even when no aliens are discovered. And me and Adam share this motivation since I believe we both feel in different ways that ecology is applied astronomy, if you will. That if, as Haeckel says, ecology is the entire, and I put the emphasis on the entire, science of relationships between organisms and their environments, there is never going to be a planetary thinking without cosmic trinity to start with. The Long L is a paper about Fermi paradox. Tell me, how many of you are familiar with the Fermi paradox? Raise your hands, please. Can anyone explain what is Fermi paradox? Very briefly. Please, anyone. Who has the courage? Right.
It's something like, from what we know about how easy it is for life to develop on all these planets that Adam told us are out there around every star, where are all the aliens? Why are we doing this?
Yeah, where are they? Yeah. That's the question that Fermi originally asked during 1950s, like at the lunch in Los Alamos. And, you know, like, if you remember Gakutetsuku now, like, he was mirroring the non-human, the more than human nature. And I think a certain relationship of mirroring is happening also in terms of Fermi paradox, because it's a mirror of human terrestrial imagination about our own future and life, whether in outer space or down here on Earth, as above, so below. So some many like to say. So the paper, the Long L paper, which is also kind of like, it is using this equation, which is an equation which was originally jotted down by Frank Drake to kind of like formalize the idea of how to estimate the number of radio communicating planetary communities of intelligent beings in our galaxy. And I think that this is also a really good framework to structure our conversation between all of you, me and Dadai. And also it's a great structure that will point us to what is yet to be done in the context of planetary thinking. So the equation, just to very briefly run you through this, there are several variables, and the main variable, of course, is like, what is the total number of extraterrestrial intelligences in our galaxy? Then there is the star formation rate in the Milky Way. There is a parameter FP, which is basically an estimation of the fraction of stars with orbiting exoplanets. And Adam already mentioned that this is going to be probably 1, meaning that there is at least one planet orbiting every star in our galaxy. But this also opens a question: what is the planet? What is the planetary? It's a big question to ask outer space scholars, and the one we've been together discussing a lot and want to discuss also with you tonight. Of course, from this moment on, problems just keep multiplying. To specify the main variable, we need to think, for example, about the average number of habitable planets per solar system. And again, what is habitability? Is it just like what we standardly assume as habitability, the presence of liquid water on the surface, or is there more to the habitability? Again, a big question, a big problem to solve as planetary thinkers. Moreover, habitability only guarantees a possibility of life's emergence, not the actual existence of life on a planet. So this variable, FL, it talks about fraction of habitable planets that actually harbor life. And so this is a totally nebulous number, so I'm not even going to introduce any numbers here because we are firmly in the realm of philosophical speculation now. It heavily depends on, for example, what we will understand as life. And there is so much going on in contemporary astrobiology in terms of how to expand the definition of life. And just as FL depends on what we understand as life, the parameter Fi also is kind of like talking about the same, but in the context of intelligence. Yeah, what is intelligence? How many of these inhabited planets have actually intelligent life? I mean, like, again, this is about guesses. This is where we are with SETI in the full philosophical mode. And that's also like perhaps what is the great about having an astrobiologist in the philosopher on stage today. With FC, the fraction of planetary communities with sufficient technological capacities for interstellar communication, things get even worse. Wow, since what does really guarantee that technology is a necessary trait of every intelligence? And of course, what is technology? Another problem to solve as planetary thinkers. And finally, the last parameter, L, the average communicative lifetime of a technological planetary communities. At least to me, this is the most exciting parameter. To talk about average lifetimes means to talk about societies, about their histories, cultures, economies. And my belief is that the longevity of planetary communities has a lot to do with maintaining the planet habitable. And this brings me to my final question. How long do we want the L of our planetary community to actually be? Or even better, what should we do to make the L intentionally longer? The answer I want to discuss starts with this quotation by Carl Schroeder, a Canadian sci-fi author, which is itself a variation to a famous quotation by Arthur C. Clarke. Schroeder's version reads as follows: any sufficiently advanced technology is indistinguishable from nature. And please, again, remember Gaku Tensoku, remember slimes, robots, ants, bees, and so on. My guess is that the key to the longer value of L lies in taking Adam's idea of major technosphere one step further. What if, just what if, any major technosphere becomes indistinguishable from biosphere? What if, just what if, we cannot find any intelligent aliens out there because even if we would see their footprint, the signs of their existence, it would be indistinguishable from the footprint of the planet's biosphere. So what if it makes no sense in the last instance to distinguish between technosignatures and biosignatures? So every night we look up on the night sky, and perhaps even today it's already dark, maybe we will have an opportunity to see the night sky. The star will mirror back to us an instruction about navigating possible futures here on Earth. Because the cosmic silence is perhaps the silence of flourishing planetary communities hiding in the plain sight. And that also brings us to our discussion. And Adam, I'm again really honored to be on the stage with you. Let's jump to the discussion together.